this on. Well, good morning, everybody. Let me reiterate just one more time our current calendar and what to expect as we wrap things up. Here is my screen, and I should be able to find us. Oh, let's just share us. That's easier. I'm going to share with you the calendar. Okay, so a couple of quick changes. First of all, I made all the homework due on Wednesday night the 6th. Your test is going to be on May 7th, Thursday the 7th, and I opened up the testing window from 8 until noon so that you would have a little extra time. So just start a little earlier than you normally do. If you, the test is not longer, it's not cumulative, it's just a regular exam like the others that you've taken. And originally it was planned to take about an hour, maybe an hour and 10 minutes. And of course, if you took 2 hours, you should have enough time, but I wanted to make sure that you have plenty of time so that you can start as early as 8 o'clock if you like. What I will need for you to do is to show up, sign into Zoom so I can proctor the test, and then you'll take the test in Canvas and answer the questions in Canvas and upload any work that supports your answers on the last question. And then I'll be able to give you a little partial credit. So you can, I'll send you an announcement about the test here coming up here shortly. You should also have all of the homework available to you in my stat lab, so you should be able to finish that up. There's some homework from section 9, 1, 2, and 3. And those are our last homework assignments. So if there's anything administrative that you think of that's bothering you, then please send me an email and let me know, and I can get right back to you and get your questions answered right away. Anything else before we get going here on chapter 9? I'm trying to see if I can see my chat. Where's the chat? Okay, there we go. Okay. Well, seeing no questions, we are going to talk about chapter 9 a little bit more today. When you were here last time, we looked at something called correlation, which is a fancy word for saying there's a relationship between two variables. Okay, and so we want to know, we're going to switch things up. So far in this class, we've looked at one variable stats. Now we want to look at two variables at the same time, and we want to ask whether or not there's a relationship between the two. Once we've sort of made a stat plot and determined what it looks like, what the relationship looks like, we would like to do our best to fit a curve through the data. And so the curve might be a parabola, it might be a sinusoid, it might be an exponential graph, but for the most part, we're going to look at linear graphs. So we're going to try to fit a line that fits the best way it can through the data. And we want to figure out what the best fit line, what that means, how to measure its, how well it fits, and how to find the equation for the linear regression line using maybe a calculator and decimals. So that's sort of our plan for today. I know that Larson has spread some hypothesis testing and some confidence interval stuff sort of throughout the 3 sections. And what I'd like to do is save all of the talk about confidence intervals and hypothesis testing until Thursday. And so once we can find the regression line, then we'll do some confidence intervals and some hypothesis testing around those ideas. And we're going to do that on Thursday. Okay, well, let's get going. I'm going to start out with some information from the book and a little bit of a review. So last time I think we worked in Desmos. This time I'd like to work on our graphing calculator to start so that you can, so I can kind of go through the steps and you can see how to make this work on a couple of different pieces of technology. Let me share. Where is it? There it is. So from the class notes, okay, we saw a couple of data sets, a couple of examples. So this is the first example from section 9.1, and it was on gross domestic product versus CO2 emissions. And so we're going to look at 2 different variables at the same time. how much does the country, is it worth, right? How much are we producing? And then what kind of CO2 emissions is that country producing? And we want to know, is there a relationship between these two things? And we suspect that there probably is. It just seems reasonable that as a country gets wealthier, that some of that wealth is due to factories and manufacturing, and some of that wealth is spent, right, on new cars, right, and sort of CO2 producing objects. And so we would think that as a country gets wealthier, that it's going to produce more CO2, right? Whereas if you were, a poorer country and folks were just living in huts and they were working on farms, they didn't drive cars, they didn't have factories, it would seem like that they would be producing a lot less CO2. So our question is there a relationship? How do we see what kind, and how do we describe that relationship? And then how do we measure the strength of that relationship? So we're looking for as GDP goes up, does CO2 go up? As GDP goes up, does CO2 go down? Or does it just do something kind of random? So to do that, we want to put this data in, use some piece of technology to kind of capture all this data and then do a little analysis of it. So that what I'm going to use is the TI-84. And you guys can kind of follow along if you like. I'm also going to use Desmos for our next example. So we're going to look at those two technologies today. You can certainly use StatCrunch, Google Sheets, Excel, and several other different kinds of calculators and different technology if you like. But I'm going to strongly recommend that you try these two and then pick one that you think you can use for the exam and kind of get maybe decent at using that particular, particular technology. Okay, so here we go. Here is the data. I'm going to set it off to the side a little bit and stop sharing so that you guys can see the calculator. And then we're going to get that data put into the calculator and see if we can make a scatter plot. Okay, so here we go. Turn on your calculator. Right, that's the kind of the first step. I'm going to see if I can zoom in a little better because mine seems to be jumping all over the place here all of a sudden. Okay, now just to get it to focus, and we should be in business. I don't know why it's having so much trouble focusing. A little bit different angle will help. Well, that didn't help. I don't understand. Okay. Give me a second here. Sorry to get seasick on my wiggling it all over there. That looks pretty good. Okay. Well, it might pop in and out, but I think for the most part, that looks pretty good for focus. So clear everything out. When I get started using stat plots on a calculator, sometimes there are some leftover graphs that I've made. So what I like to do is turn everything off, clear everything out as I start a new problem so that I don't have kind of two problems mixed up at the same time. So go to y equals and clear out any equations that you have graphed. Okay, you might also notice that my plot one up there is highlighted, and that's because mine's turned on because I already made one this morning. Right? But in general, it would be, if you push enter, then it would be turned off. So now all my plots are off and all my equations are erased. So I should be good to start a new problem. So to do that, we're going to use the stat button. The stat button, right? 2 down, 3 in. We're going to push this one a lot. We might push distribution from time to time, and we might go second stat to go to our list. Okay, so but I want to be able to see the screen. So I'm going to scroll it down. And then I'm going to push the stat button. And in the stat menu, you can do a few things. You can set up your editor. If your list gets screwed up or something, you can reset everything back to scratch. So you could just say set up editor, right? and it'll get everything back to normal. You can also clear individual lists or sort them, but for the most part, what we're going to want to do is edit our lists. So if you push edit, you'll notice that I already have some data typed into the list. That's because I didn't want to have you guys have to wait for me to type it all in. That's a big part of this process. So being able to type the things in accurately and correctly is going to be part of your job. Of course, if you're doing it on the homework, you'll just get a red X. Something will be wrong. You can go check your typing. On the test, you're going to have to do the best you can. If you make a typo, then you're going to have the wrong answers. But if you upload your work, right, the work that you did to support it, then I'd be happy to look through it and give you partial credit. So if you do the right thing, but you made a typo, then you just get like maybe 1 point off or something, and you get all the rest of the problem right. If you don't support your work, well, that's up to you. If all you do is give me the multiple choice answer, then it's right or wrong. So type carefully. Yeah. All right, so my first step was simply to type in the data. So 1.8, 1.3, 2.2, 1.5, etc., right down this list until I got all my X's. And then I'm going to put my CO2 emissions here in list 2. Now, of course, you can use other lists. You don't have to use list 1 and list 2. You could use 3, 4, 5, 6. You can rename these lists if you want to. But for the most part, I just use the default. And I like to clear everything else out so that I'm not confusing one problem with the next. Okay, so this is 602 million metric tons of CO2. And then we go on down the list here. Our last value was 1157.7. So type those into the list. Okay, so if you're following along, I don't know if I've talked long enough to let you get it in there, but maybe we should be close. One of the things that you might do with this data are the things that we did way back in chapter 2 and 3. You might want to find the mean, the median, the mode, the standard deviation, okay, or any of those other values. To do that on your calculator, you can calculate them individually or just all at once. And I like the all at once feature. So you'd say stat, and under the stat menu now you've edited, so you've already put them all in. So go over to calculate, and you'll notice that you can calculate 1 variable stats, 2 variable stats, and a bunch of regression lines. Linear regressions, quadratic, cubics, quartics, sinusoidal, exponential, logistic, okay, a bunch of different things that we can do. We can even at the very bottom do a manual fit, meaning we can just estimate where the line goes ourselves. So we're going to explore all of these regressions today. Okay, and in particular linear regression, right? So let me go back up to the top. If you say 1 variable stats, now that you've got stats in list 1 and list 2, you'd have to tell it which list. So we could say calculate 1 variable stats, and to do the list, you'd say second list, and then you'd say do it for list 1. And it, of course, would find the mean and the standard deviation and the 5-number summary down here at the bottom, just like it did before. So you could do that for list 1, and you could do that for list 2. If you want to speed things up, you can say stat calculate 2 variable stats, and it'll just do both of them at the same time. If you don't tell it the list, it'll default to list 1 and list 2. And so here they are. So the mean of the X's, which it assumes is list 1, is about 2.29. So about $2.29 trillion in GDP. If I go way down here to the bottom, who's that? Diana? Good morning, Diana. Okay, if I go down here to the bottom, it says here are the Y's. So the Y's are going to be by default in list 2. And it says my Y's are going to be CO2 emissions, and here we have 512 or 513 million metric tons. And if you need any of these calculations, of course, it does all of them all at once for you. Okay, so what do we want to do? We want to look at the relationship between X and Y. So we want to make a stat plot of these and see a scatter plot of these and see kind of what it looks like. So what you're going to do that is you're going to use this stat plot button. It's right next to it's right above the y equals. So you're going to say second stat plot. And you can make up to 4 plots at once, but I just do them one at a time and leave the other ones turned off. Oh, sorry, 3 plots at once. Notice it's defaulting to list 1 and list 2. So I'm going to select it. I'm going to turn it on. And of course, I can make a lot of different statistical graphs. I can make a histogram or a box plot. We want to do this first one right here. It's called a scatter plot using list 1 and list 2. If you have multiple graphs, you might want to use a different mark, like a different symbol to indicate the points. I just use the boxes. It seems to work pretty well. Okay, and so now everything is all set up. So we would want to go look at our plot. So we push the graph button. But oops, probably some of you, when you push the graph button, got just this, right, with no data. That's because by default, your window zooms to -10 to 10, -10 to 10. And of course, our CO2s are over there around 500 or so. And so you're going to need to adjust the window to be able to see the data. So you can push the window button and you can adjust it manually. The X's look like they were going 0 to 5, and the Y's look like they were going about, I don't know, 200 to 1200. And so then you can push graph and then you should see your data. One other nice feature of the TI is that it can kind of zoom to the data for you if you don't want to adjust the window yourself. You can push zoom and then you can go down, it's number 9. You can go down to zoom stat, and if you select zoom stat, it'll adjust the window so that all your data points are nicely inside the bounds of the window. So there it is, there's our stat plot. And so now that we're looking at the dots, then the question is, do they seem to be related or not? In other words, if X goes up, does Y go up? If X goes up, does Y go down? Does it follow a curve? Or are they just scattered all over the place? And in this case, I would say, well, it looks like they are kind of related. The bigger X's are bigger Y's. So I would say there's a positive relationship here. Because if I fit a line through that data, of course, it would have a positive slope. And, but it's not exactly a line. So there's not just one line that I could make that would hit all of these points. Right? If I drew a line that hit these 3 points, these first 3 points, I may very well, the 3 in the middle, I might be able to get it kind of going straight through. I might be able to hit 3 of them, but then some are going to be above and below the line. The question is, are they scattered around a line or are they just all over random? And in this case, I'd say they're kind of following a line. It'll be our job then to find a line that goes through these points and misses them by the least amount. That's kind of what we want to do today. Okay, that is a stat plot. Questions about making a stat plot? I think we did that mostly last time. This is kind of a follow-up. If I share my screen with you back to the notes, then here's the one, right? Here's the one that the book got. And I think that's pretty close to ours, looks very similar. And so Larson agrees. He says there appears to be a positive linear correlation. Now, how strong is it? By how strong, we mean how close are those points to a line? Like if we put a line through them, how close could we get the line to all those points? And we'd say, well, we could probably hit 3, right? I think we could hit these 3, this one, and this one. My mouse on there, yep. Okay, this one, and this one. I think we could get pretty close to those 3. It would go zooming up here, it'd be pretty close to that one. The others would miss, but they'd be pretty tight to the line. I'd say it seems to be at least a medium, if not a strong relationship. So that judgment about how strong, it's pretty subjective. If they seem to be along the line, you'd say strong. If they don't, you'd say not so strong. And what we'd also like to have is a way to measure that strength of that relationship, a number that we could say, if this number was bigger, it would be stronger, right? So we're going to work on that as well. Okay, so what do? What you do next is another one, right? And so our next example is going to be the geyser, Old Faithful, in Yellowstone National Park. It erupts, right? About every hour to hour and a half, it looks like. So looking at the data, it erupts about every hour to hour and a half. And if you happen to be standing there enjoying it, you can watch the eruption for about, I don't know, let's see, between 1 and 3, maybe almost 5 minutes, yeah? Between 2 and 5 minutes. So it'll squirt, I guess mostly water, up in the air, right? And steam for 2 to 5 minutes. And then it kind of reloads for an hour to an hour and a half, and then does it again. And fairly faithfully, I would guess, since it's called Old Faithful. So the question is there a relationship between the length of time for which it erupts, and the time it takes between eruptions? So in other words, if it erupts for 5 full minutes, does it spray all of its water up in the air and then it takes longer for it to reload, which seems to make sense, right? If it does a short burst, then it seems like it would be able to do another short burst in less time. So you'd have to wait less time. And so we might want to know, is there a relationship between these two? And if there is a relationship, is it a linear relationship? Does it go up like a line? And if it goes up like a line, well, what line? And then once we have the line, we should be able to say, okay, I got here right on the tail end of an eruption, right, as I'm pulling up to the parking lot. I asked somebody and they say, well, it was a 3-minute eruption, right? Can I use that line to make a prediction about how long I have until the next eruption? So you'd say about 3, well, look at this. This is 2.82, took about 73 minutes. 3.13 took about 76 minutes. So it looks like about 75 minutes or so. So I have an hour and 15 minutes. So I can go explore the park. I can drive over and get a hot dog and come back and then watch the next eruption. Okay, so what do? We have to make another scatter plot, and then we're going to put our regression line on there. So scatter plot, check it out. Larson gives you some directions in the book for how to do what we just did, right? You're going to type in all this data into list 1 and list 2. You're going to turn on your plot, and you're going to make a scatter plot. So you can go through that example again using your calculator. What I would like to do is switch technologies and see if we could do this in Desmos, because Desmos does such a nice job making graphs. Okay, so I'm going to stop sharing this. And I'm going to go over and share. Where did my Desmos go? I don't know what happened to Desmos. Give me just a second here. Move this out of the way. Desmos. Okay, here's Desmos right here. All right, now I have to go to this and share Desmos share. Okay, there you go. You guys have, hopefully you have that. It's on my iPad, so hopefully you guys can see Desmos. And so now what we're going to do is we're going to put in all the data. So I did this a little bit ahead of time so that you guys wouldn't have to wait for me to put in all the data. But let me get started, and then I'm just going to reload the graph that I already made. So to do that, you need a table. You need a place to put it. So you're going to hit this big plus, and you're going to add a table. And then you're going to start putting in the data. So you guys, if you've got your book up, you can see it. I'm going to drag mine off to the edge there so I can see it. And then you would put in 1.8, right? 1.82, 1.9, 1.93. I'm going to just stop right there and put in some Y's, 56, 58, 62, 56. Now, of course, you're going to have to put in the whole list, right? All of the values. I'm just going to reload them in a second. How come I can't see them? Well, because again, you have to adjust your window. Now you can use your mouse and scroll out so that it looks like they're way up here. Or you can push the graph settings and adjust your window just like you did on your TI. So we said 0 to 5, and we said Y should be about 200 to 1200. Is that what we said? No, that was the other data. We said 40 to 100 minutes. And we said that the eruptions are going to be about how long? Oh, 2 to 5 was actually pretty good. 2 to 5. So where is everything? Interesting. Oh, I only put 4 in. That's why there's only 4. Okay, there's the 4. And so based on those 4, right, you'd say, well, does it look like a line? Can I make a line hit those 4 dots? And you go, well, I'm not really seeing a line. A line might go kind of through these 3 dots pretty good. But then what about this one? Or are those just scattered around? So maybe a very small sample would not be enough for you to get a feeling on the type of relationship that we have going on. So you'd have to make a bigger list. So let me go ahead and grab the bigger list. I'm going to open Old Faithful. So I already typed it all in. So here's my big list. There's all of the values. I typed them all in for you. And I already did a little zoom. So here is my scatter plot using Desmos now for the Old Faithful data. And so, in fact, screen share, desktop share. So if you can see this, right? Here was the one on the calculator from the notes. And here's ours using Desmos. Boy, those look pretty good. Those look pretty much the same. Okay. Questions about making a stat plot or a scatter plot?
No. No.
No? We're feeling okay? All right. So our next job is to try to get a line that goes through this data, okay, a linear regression line. Technically speaking, you could look at this data and you could say, does it look like a line? Does it look like it's in a line? Or does it look like it's in a curve? And if it were in a curve, you might want to try to fit a curve through the data. We're going to start by trying to fit a line through the data. Okay, so the first line that we might try is the average. So I might say, well, I don't know, what is the average amount? So to do that, I would have to average all my Y values. So I did a little work on this ahead of time. But right down here, you would type the mean of the Y1 values. Okay, and you would get an average of 74.88. So this is saying the average time that you have to wait between eruptions is about 75 minutes. And of course, in Desmos, you can calculate all the other regular 1 variable and 2 variable statistics. So you can find the mean, the median, the mode, all that other good stuff as well. So what I'd like to do is graph a line, right, that's equal to the average. So I'm going to graph a line. First of all, I want to save this number so I can use it. So I'm going to say Y sub m, the mean, was 75.88. And that way I can use this in other calculations. So the first thing I want to do is put a line through the data. So I'm going to call that line L sub m, like line for the mean. And I'm going to say Lm of x is equal to the average. I'm going to turn it on so you guys can see it. So there is the average. So the question is, does that line fit the data very well? And you'd say, no, right? I mean, it hits this one point. That's pretty close to the average. But then all these points are above average, and all these points are below average. In fact, the points to the left are below and right are above. This suggests that there's actually a positive correlation between the data. So instead of using the average, right, we want to use a different line. So let me move this out of the way. And let me try line 2. Okay, so for line 2, this is line 3. We'll do that one in a minute. For line 2, my second line, I'm just going to estimate where it goes. I'm just going to guess, okay, or guess and adjust. So I'm going to call line 2, okay, I'm going to call line 2 M2 for the slope of the second line, X plus B2 for the intercept of the second line, and I'm going to make a slider for M2B2. I'm going to turn it on. So where is it? Well, there it is, way down there. You see it? It's flat. And so now what I want to do is I want to change the slope until it seems to be, sort of going through the data. So there now it's going through the data. But as you can see, it's too steep, right? So the angle of the data that goes through would be less steep than that. So what I'm going to do is I'm going to slide my line up a little bit and then tip it down some. So it looks like it needs to go up some more, and I need to tip it down a little bit more. And then it still looks like it needs to go up a little bit more. So it's looking pretty good, sort of right about there. And we can zoom back in on it again so we can see. So I'm going to argue that this blue line is a lot closer to our data values than the average, the line where the average was. We would say that a lot of the variation in the Y values is explained by this line called the linear regression line. Well, this isn't the linear regression line, our estimate of the linear regression line. So what did we get? I got 12x plus 36. So my slope is 12 and my intercept is 36. So in terms of the Old Faithful data, the intercept is the value you get when you plug in a 0. So 0 means if the eruption doesn't happen at all, then I would expect to have to wait 36 minutes. The slope is the units of Y over the units of X. So the units of Y were the time between eruptions, and the units of X was the time of the eruption. So basically what we're saying is, for every 1 minute that Old Faithful erupts, you would have to wait an additional 12 minutes before the next eruption. So if it was 1 minute long, you'd wait 12 minutes. If it was 2 minutes long, you'd wait 24 minutes. If it was 5 minutes long, you'd have to wait 5 12s or 60 minutes. And so just by sort of eyeballing it, I would say that this line goes through the data pretty well. In fact, but it only hits 1, 2, and it kind of goes right between those. It looks like it hits only 2 of the data points right on, and the rest are a little bit above and below. So the question is, how much does it miss by? And we can just do a rule of thumb. We could just kind of look at it and say, well, less now than it did before. But we'd like to be able to measure that amount. Okay, and so to do that, what we're going to do is we're going to take the amount that it misses the line by. Okay, and so let's do this for the black line first. I'm going to say up here in my table that my y value minus my mean. This is how far away from the mean the y value is. And in terms of the picture, it's how far above or below this black line my values are. So let's get this other one off of here for now. Okay. And so now what I'm saying is, well, look, this one's way below, 19 below, it's way down here. And this one over here is 15 above, so this one's way up here. Okay, and so some are over and some are under. So you say, well, I wonder what the average amount of over and under is. Well, if I add all this up, because it's the average, it'll add up to 0, right? The over and the under cancels it out. So we have two choices, just like we did back in the good old days, back in chapter 3. We can either make all those distances positive by taking the absolute value and calculating the mean absolute deviation, or maybe if I can, maybe if I can just open that window up a little bit more, we can square all those values, which would also make them all positive, but it would give more weight to the values that are farther away from the mean. So the outliers would play a more important role, right, in the direction our line is going. Now, we can add these all up and divide by how many there are. And I think there were 24 or 25 times in our list. So we can add all these up and divide by 25. And we will get the average amount that the points deviate, the average squared distance from the average, okay? Or the standard deviation of the points. Okay, so let me see, I did that in Desmos here. Here it is right here. So let me, I don't know, I'll just leave it down here. I'll move it up so you can see it. Okay, so here's what I did. It's some funny notation. You're gonna have to play with Desmos a little bit. In fact, earlier today, I kind of couldn't get it to do what I wanted, and I had to play with the notation a little bit. But here's how it works. Y1 of n is gonna be the nth green dot, right? The nth data point. And what I want to do is I want to say, how far away from the line is this point? So I want to take the difference. But in this case, I don't want to use L3. I want to use L, right, M. So this is how far away from the average line, here's LM, squared, add them up, that's the summation notation, and divide by 25. And so I get a number, okay? And so the average squared distance from the average turns out to be about 182. That's a lot of missing, by the way. 182 is a lot of missing. So what we want to do then is say, well, you know what? If I, instead of using the black line, I use this blue line that we use to estimate, the one we put through here ourselves, then I'm going to say, how far away from our blue line is it? Well, the blue line I called L2. So we'll call this L2 now. Notice that now when I take the average squared distance from the average, I end up with 8.4. So we would say that the points are a heck of a lot closer, right, to the blue line than they were to the black line. In fact, it went from whatever that was, 162 down to 8. The question is this as low as we can possibly get it, or could we get it a little lower, right? And so what would we do? We would play with our line a little bit. Check this out. It was 8.42. So maybe if I move it up a little bit, does it get better? Oh, look at that. Now it's 7.94. So I'm actually a little closer to the points now than I was before. And now let's make it a little steeper. Nope, it's getting worse. Okay, a little less steep. Oh, getting worse. Okay, that one looks the best. Okay, now maybe I can move it up and down. There's 7.8, so that's a little bit better. And then this is 7.9, that's worse. And this is 7.9, that's worse. So that's looking pretty good, right? The question is that the best one? And I could play around with the sliders and I could adjust the resolution on the sliders so that we could just keep playing with this. or we could just let the calculator, let Desmos find the line that fits the best for us and tell us which one it is. You can do this on your calculator, and you can do this in Desmos, and here is how you do it. So what we now want to do, I'm going to move this down. What we want to do then is create a model, okay? Create a linear regression line. And to do that, you use this, tilde. So y1, x1 are up here. Those are the names of my x and y coordinates of my points. I'm going to say y1 is approximately some new number. I could have just called it m, but I already used m. So I'm going to use m3 for the slope of our third try. And then you say x1 plus b3, which is the intercept for our third try. Okay, and again, you can name these anything you want, but that just seemed reasonable. We had already used M2 and B2 and M1 and B1, so I'm going to call them M3 and B3. And then Desmos goes off and does its thing. So it goes, and it says, hey, you know what? If your slope is 12.48 and your intercept is 33.68 or so, it's going to fit even better than the one that you came up with. Okay, so what did we get? We got 12 and 35.3. And what did Desmos get? Desmos got 12.48 and 33.68. And then I said L3, our third line, is the M3 that it calculated, X plus B3. I'll turn it on so you can see it. Boom. Okay, so ours was the blue line, and Desmos got the red line. And it turns out that the red line fits just a little bit better than ours. But you can see that just by estimating the line through the data, we did a pretty good job. I mean, we were pretty close. Okay, so let's see how much better Desmos did than us. We got 7.897. And now if I change this to Desmos's line, L3, we get 7.638. So just a tiny bit better fit. It turns out that using some calculus, you can prove, and you can actually do Desmos's calculation for the regression, and then you can prove that this is the line that fits the best, right? It's a maximum minimum problem. So you want to take the derivative, set it equal to 0. Okay, and you guys can look at that in a calc class somewhere down the road if that interests you. As you can see, our blue line was so estimating using the blue line, pretty accurate, right? Accurate enough for most people. And if you want the exact one, then let the computer, calculate it for you. Okay, so there is our linear regression line using Desmos. That was kind of quick. You guys can come back and look at this again. And certainly if this is the tool that you choose, you should play around with it a little bit. You don't need to do all this sort of super elaborate stuff that I did. I did that for you guys. Let's do a quick one from scratch so that you can see just the bare bones. Okay, I'm going to say, give me a new graph. And then I'm going to put in our data from before. So our original data was on the GDP. So let me put the GDP data in here and show you that, yeah, it's possible to do this kind of quickly if you just want the quick and dirty stuff. All right, so new graph. Make a table. Once you got a table, put in your values. There's no fast way to do this. You have to type them. 2.4. If you're using Excel, you can probably cut and paste them. But for Desmos, you're going to have to actually type them in. 0.9, 1.4, 3.0, 4.6. I'm just going to use this data set because it's a little bit shorter. 604.4, 434.2, 544.0. 544.0, 370, 0.4, 742.3, 340.5, 232, 262.3, 441.9, and 1157.7. Okay, where are they? Next, we have to zoom the window. I'm going to just drag down on my mouse until I see them. Oh, there they are, way up there. Okay, and how come the X's aren't very spread out, the Y's are very spread out? Probably want to go to graph settings and change the window. So on the window, I'm going to go 0 to 5. And for the Y's, I'm going to go, what did we just say these were? 200, that's not 200, 200 to 1200. Not 12,000, 1200. Okay, there they are right there. Beautiful. Questions? There's the stat plot. Okay, got the stat plot. So next, we want to do our regression line. We want to fit our line through the data. So to do that, we're going to say the Y1 values, here they are in the list, Y1, okay, are approximately slope, I'm going to use MX1 for my X1s, right, plus B. So MX plus B. M, traditional value for the slope, B for the intercept. Boom, it put a line through there. Last time our regression line was red, so I'm gonna make red for regression line. Here is our slope, pretty close to 200. Here is our intercept of 56. We could have certainly done it by sliders and guessed, okay, but we just did it by Desmos, just quickly. Questions about that? I think as much as we did right here, it's going to be enough to answer most of the questions on the homework. So you don't have to actually do the calculation for exactly how much to measure the amount of error like we were doing earlier. They're just going to ask you for the regression line. And that's how you make it. Okay, one more thing before I call it good. Let's go back to the calculator. And if I can get it to zoom in and turn it on, we're going to say, I want to put my regression line through this data that we just did. So I'm going to say stat, and I'm going to say calculate, and I'm going to go down here to linear regression. Notice that they use AX plus B instead of MX plus B, but that's okay. It's the same, A instead of M. Do the linear regression. Boom, it does it. And it says the slope is 199.53, the intercept 56.03. That's what we just got. You can read, we're going to talk about these next time, how well it fits, the correlation coefficient, and the coefficient of determination. We're going to talk about those some more. You can start to look at them this week. And now all we got to do is put our line on there. So I'm going to push Y equals. Now, depending on your calculator, it might put it in here automatically for you if it's a little bit newer. But for me, I'm going to have to push VARS, statistics, equation, and then put the regression equation in there and it'll type it for me. And then when I push graph, check it out, boom, there's our line through the data using the calculator. And it looks pretty much exactly like what we got using Desmos. So I think the calculator's a little...
Can you just redo that real quick?
You want me to do it one more time?
Yes, please.
Okay, so to get the regression line, you're going to push stat, right? Stat button right here. And then once you get the stat, arrow over to calculate. And then go down here to regression line, the linear regression. We can talk about other kinds of regression later. But for now, do a linear regression number 4. And then if you put your data into list 1 and list 2, which is the default, it defaults to those. So you can just push return. And it tells you the slope is about 199 and the intercept is about 56. So all that's left to do is to graph it, right? And I don't want to type these numbers remember what they are and try to type them by hand. So here's the funny sequence of buttons that you're going to push, okay? you're going to push y equals, because you want to graph the line. Let me clear it out of there. And now you want to, sorry about the focus. Every time I touch a button, it refocuses on my finger. You got to push the stat button. So here you push stat. Nope, sorry, I lied. Push y equals. You're going to push, it's a variable that you want to type in there. So 3 down, 4 in is the vars button. Right here, vars. So push vars. And then if you go down to number 5, we were calculating statistics, so that should make sense. And what we want to type is the regression. Look at all these things we have in here. The mean, the number, the standard deviation. If you need them in a calculation, they're all right here. But what we want is the equation. So go over to equation. And then number 1 right there is the regression equation. So if you select it, then it'll type the equation for you right after the y1 equals. So you don't have to type those numbers yourself. And then all that's left is push graph, and there goes the line through the data.
Awesome.
Did that help?
Yes, thank you.
Okay, I think that there are some instructions in the book. So you can, so if that still went too fast, you can look at the book. But the book kind of explores several different technologies. So if it doesn't give enough detail, then what I would do is just go to Google and type whatever calculator you have, TI-84, linear regression. And you should get like all kinds of stuff that'll kind of take you step by step through it.
Okay, thank you.
Okay, well, that was a lot of stuff and a lot of technology kind of back and forth today. I think that's probably enough for us for one day. I'm going to, well, see, do you guys have any questions? Anything really bothering you?
No.
Okay, then I'm going to let you guys try a few of these in the homework. Okay, and see if you, and then, but try some on your calculator, try some in Desmos, figure out which one you want to use, you know, most of the time. And then I'd probably just focus on that particular technology. So if you like the calculator, just use it. And then kind of collect some questions. If you have any questions at all, kind of write them down on paper for me so that, excuse me, on Thursday, we can talk about a little hypothesis testing and confidence intervals around regression lines. We're going to do that a little bit and answer any questions you have, kind of review questions you have for the test, because Thursday will be our last class meeting, and then it'll be a week from then and we'll take the last exam. Sound okay?
Yes.
Okay, then we'll have a great couple of days and we will see you guys on Thursday.
Bye. Thank
So,
you.